Welcome everyone to today's webinar. We're going to wait just a few more minutes for everyone to join, and then we'll get started. So while we wait, in today's session, we're going to cover the use of Spark for memory safety. Today's topic builds upon the previous Spark webinar. We're going to illustrate how the Spark language, Spark's flow analysis, and Spark proof work together to provide proven guarantees of memory safety. Please note that this event is being recorded. The link will be available via email after the webinar has concluded. You won't be seen or heard, but if you're not comfortable with the recording, we invite you to sign off now. Let's get started. I'm Tony Aiello, one of the product managers at Adacore. I'm responsible for Spark. During today's presentation, if you have any questions, please use the tab at the bottom right of your interface. We'll have a question and answer session at the end. Now, before we dive in and talk about memory safety with formal proof, I'd like to say a few words about Adacore. Adacore is a tool provider for high-integrity software. We were founded in 1994 and have about 150 employees worldwide. Our technology is used in a wide variety of projects all around the world. We bring expertise in embedded and high-integrity platforms. At Adacore, we develop toolchains for a growing number of programming languages. We support Ada and Spark, C and C++, and now Rust. Our goal at Adacore is to be your one-stop shop for high-integrity and safety-certified embedded needs. Without further ado, I'll hand over to Yannick Moy, Adacore's head of static analysis and one of the lead developers of Spark.
So hi everyone. I'd like to start by explaining what we mean by runtime errors in Spark and how this relates to memory safety. So let's look at this very inconspicuous piece of code, which is really just on one line, computing a value, here an arithmetic expression p divided by q, and assigning it into an array A at an index which is also computed as an arithmetic expression I plus j. And if you look at this one line of code, just try to imagine everything that might go wrong that might be characterized as a runtime error. And if you guessed right, there are 5 possible runtime errors in this simple line of code. So first, looking at the index, just computing the index I plus j might overflow the underlying machine integer used to hold this result. Then even if there's no overflow, the result might still be outside of the bounds of the array A, so might write out of bounds. And then if we look at the expression which is computed to store inside this array, q might be null, so that might be dividing by 0, or with very special values of p and q, namely p being the first integer of the type and q being -1, this division might end up overflowing also the machine integer. And even if there's no machine integer overflow or division by 0, the result might still be outside of the bounds of the values expected in array A. And so all of that could occur in this unsuspecting piece of code. And we're especially worried about the first two, so the errors that might occur in the computation of the index, because there are cases of violations of the memory safety. We could end up writing outside of the array A here. And memory safety is very important. If in case of violation of memory safety, we know that there could be exploitation of security of the program, which lead to violations of confidentiality, integrity, availability, any properties of the security of the program. So we want to ensure that the memory safety is preserved in our program. We can do that with Spark. So let's look at the editor here. So I've selected GNAT Studio this time instead of VS Code. And here is this declaration of the procedure sign with the types that are involved. So an array of indexes over elements here. And if we call Spark on this code, indeed, it's going to point out at the 5 possible errors that I mentioned. So 2, the overflow index check and on the index, and the division by 0, overflow check, and red check on the value. And note that the tool provides you with a number of additional information, when it says that something might go wrong. So it points at what exact check in terms of low bound, high bound might fail, the reason for the check, and even sometimes a possible fix, or how to add the precondition to this procedure to avoid this problem. So coming back, we'd like to differentiate runtime errors and runtime checks. So there are many possible kinds of runtime errors in Spark. Some that we just saw, numerical errors when we divide by 0 or have an overflow on scalars, or values out of the range of their type. There are memory safety errors, so when you go outside of the bounds of an array, the overflow, or they reference a null pointer or casts in the wrong type. There are also type safety errors, just reading an initialized value, for example, or violating the type constraints out in addition to the range that we just mentioned. And there are errors when you're using tasks, so related to safe concurrency. If you deadlock or have race conditions between tasks. And finally, there are memory availability errors when there's not enough memory to complete the execution of the program. So that might be because you overflow the stack or the heap, or because you're leaking memory or the memory becomes too fragmented. And note that not all of these runtime errors lead to a runtime check. So runtime check is something that is inserted by default by the compiler to produce a safer executable. So that's the case for a number of these runtime errors. In that case, a runtime exception will be raised when you run the program if the problem is hit. But there are cases like reading an initialized variable where there's no runtime check. There are other cases like race condition. So when multiple tasks access the same unprotected memory, or leaking memory that don't lead to runtime check. What's important is that all of them lead to a static check in Spark. So the tool will issue statically a message if there's a possible problem. All of them except for the memory availability. So stack overflow, heap overflow, and fragmentation should be checked separately. But note that Spark has checks for memory leaks. So how does it work? Spark does a verification unit by unit. So that's the 2 files that we typically find for a unit, the specification, ADS file at the top, and the body ADB file at the bottom. And we're including here in this verification all the specification of the dependent units. So all the units that are needed to analyze and compile this unit. In both the specification and the body, you will find static checks. And the Spark tool is going to extract from each of these static checks in each of the functions which it analyzed separately, a formula called the verification condition that explicits what is needed for the check to pass. And so for both the spec and the body, we will get these verification condition files that are sent to provers, automatic provers. So we have 4 embedded in the Spark technology, AlterGo, Colibri, CVC5, and Z3 in this picture. And depending on the answer from these provers, if one of them manages to prove that the check is safe, then we know it's proved. In the contrary, none of them succeeds. The user will be given a check message stating that there's a possible problem either in the specification or in the body. So obviously, we'd like to prove all the checks, the static checks related to memory safety. But that's not all. Indeed, when doing this proof modularly, so function by function inside a unit, the context for the proof includes everything up to the point where this check might fail. This means the precondition of the enclosing subprogram, which gives the starting point for the analysis. This means the effect of all the statements up to that point, and this means also all the passing static checks up to that point. The nice thing is that all this proof context makes it very easy to prove memory safety, but it also means that all the static checks related to runtime errors, other runtime errors not directly proving memory safety, should be proved too. And note that the contract on types and subprograms are also part of this context, so this means that the static checks related to this contract should be proved too. And here, Spark really operates by divide and conquer approach. So instead of a gigantic memory safety check, it breaks that down into numerous, very small checks that are amenable to automation. So in the end, it's not more work, but it's less. And that's what we call the silver level. So proving all these runtime checks, which includes memory safety. So in this silver level for proof in Spark, we're focusing on the absence of runtime errors with memory safety. There's a special case for proving absence of uninitialized reads because it's proved by a combination of analysis. We'll see that. We may need simple contracts for this modular proof. That means some precondition and some postconditions on subprograms, as well as some constraints, predicates, and invariants on types. And here, we advise that we put contracts on types whenever possible. Why? Because type contracts apply implicitly everywhere the type is used. So in general, when we have a choice between contracts on types and contracts on subprograms, we will prefer contracts on types. So let's see that on the examples that we saw before. So now we can look at a fixed version, if you will, of the program that we saw before with the same body, but a precondition here. So essentially putting in the precondition the suggestions of the tool. And you have these 5 lines of precondition, so constraints on the parameters for a sign that ensure that none of the 5 errors that we saw before are possible. And here, if we call Spark on this program, there are no errors, no messages, and we can ask the tool to explicit all the things that it has checked. And here we can see that the 2 checks on the left-hand side have been proved, and the 3 checks on the right-hand side have been proved too. But there was a lot of preconditions here, and there's a better way. So we can look at this other variant where we have refined the type index here, which means that we don't need as many preconditions for procedure assign. We just need to state that the addition is going to be in the range of the array, and that the quotient Q is not 0. And with this much simpler precondition, now Spark still proves everything in this function, in this procedure, and it has even fewer checks to prove, because by typing, the checks cannot fail. Of course, there's a runtime effect of checking, whether it's related to runtime checks or assertions. And to show that on an example, we called 1 billion times this function with the 5 preconditions that I showed before, compiled at a reasonable optimization level 01, and measured both the object size generated by the compiler and the running time of this application on a Linux laptop. On the left-hand side, you can see the results without any checks or assertions. So that's obtained by passing the switch gnat-p to the compiler. And you get the optimal results here. In the middle, you compile with checks, but without assertions. And you can see that there's an impact in terms of increased memory size for the object and increased running time. But this run is protected against runtime errors. In particular, it's memory safe. And on the right-hand side, you have the same, but compiled with assertion. So passing in the switch gnat-a to the compiler. And you can see again that there's an increase in size and running time compared to just adding checks. The nice thing to consider is that for proven Spark code, it can be compiled without checks or assertions. So you get the results on the left-hand side, the optimal results, but with the guarantees that all the checks will pass. Now let's look at the absence of reads of initialized values, because it illustrates a general approach in Spark towards usability. First, Spark has a default data initialization policy to make verification of these checks automatic. It forces all inputs to be fully initialized when entering a subprogram, and all outputs to be fully initialized when exiting a subprogram, as well as all arrays to be fully initialized when they are assigned, so that it's considered initialized when read. So that means using aggregates when assigning to arrays. So that's a simple policy, but it's not always convenient because it may force useless initialization to stick to the policy. On the other side, it doesn't require any user work to get the analysis done. In those cases where it's not convenient, it's possible to relax the policy on selected types and objects. And in only those cases, for these objects, there will be verification conditions, so formulas generated and prover code for showing that the values read from these objects have been initialized. For that, we have a specific aspect, relaxed initialization, to put on such objects and types to specify that they are subject to this relaxed policy. And we have a ghost attribute initialized to state when we want part of this object to be initialized. And it's a general policy in Spark, general approach, where we want the defaults to be safe, but also put the less work on the user to be the most user-friendly, and still have the possibility to relax the constraints that are imposed in the default case. But in that case, when you relax the policy, there will be more work for the tool, but in particular, more work for the user. So let's see that on an example. So here we have an array tab of 20 objects, and we are initializing it by bits. So first initializing the first index of the tab, then the index 20, and finally the index is in the middle. And you can think that there could be computations intermixed with that. So we can try to show that this holds, but here the default policy doesn't hold. So since we only initialize one cell of the tab, it's not considered initialized. And so even though we're just reading the same cell that has been initialized the previous line, the automatic analysis here doesn't manage to detect that this is safe. So the way to make the tool realize that it's okay is to state that tab is subject to this relaxed initialization. Let's also ask the tool to prove that after all this initialization, indeed tab is initialized, since we are doing this more finer grain modes where we need proof to get that information. And here, all the information is in the subprogram. So initialization is proved when reading tab of 1 here, and tab is proved to be fully initialized using this attribute initialized after this sequence of assignments. So that was the case because we were directly initializing tab in the function. So let's see what happens if we go through an update function. So update procedure here. And here update takes a table T, which is also subject to relaxed initialization. And let's not worry about the postcondition for now. So if we just do that, the first read of tab here is safe, as well as passing tab in update here. But the tool cannot show that tab is fully initialized after the update, because we didn't state what was the effect of calling updates on the initialization of tab. And so we need here to specify that after calling updates, well, first, all the cells in the range I to j, which are parameters to updates, will be initialized in T. And for all the other cells in T, they will keep their old initialization status, using here this T all to refer to the previous value of T on entry to update. And when we do that, then the tool checks that update satisfies this contract. and can now deduce that after the sequence of updates to tab, directly through assignments or by calling updates, tab is fully initialized. And that's a general approach to proving absence of runtime errors and memory safety. We need to consider which contracts are needed to prove this absence of runtime errors. So let's do that considering a simple API of stacks. So with a type for stacks. So here on the left, we just have a type content table for the content of the stack and a marker top for the top of the stack with this field content of this type content table. Very simple API to push an element on the stack and a function to pop the element of the stack that returns it. And you can see here that this function also modifies the stack. So for a function to have an effect in Spark, side effect, we can now do this in the latest version of Spark Pro by adding this aspect side effects on the function. And we would like to know which contract to write, both on the type and on the API, to prove absence of runtime errors in the implementation of push and pop, and in the client code, creating a stack and pushing, popping values from it. So the first thing to do is to add the necessary contracts on the type. So we can use the relaxed initialization aspect that we just saw to state that values of type content table are not fully initialized always. And then a predicate on stack that relates first the value of this marker top, so that it's either 0 when the stack is empty or up to 20 when the stack is full. And relates the marker with the initialization status of content, of this field content. So we know that at any time, content is initialized for all values of indices between 1 and top. And just note that here we're using a ghost predicate instead of a regular predicate on this type because we're using in the predicate this attribute initialized, which is a ghost attribute. So that's not sufficient for proving the safety of push and pop because push and pop are going to add elements or remove elements from the stack. So for being able to do that, we need a precondition. So push should only be called on stacks that are not full, and we can state that in the precondition. And pop should only be called in stacks that are not empty, and we can also state the same in the precondition of pop. And you can see here that you have a definition of is empty and is full, which relates to the actual content of the stack, so this top marker. And with that, that should be sufficient to prove that this calls the implementation of push and pop is safe. So that's not sufficient to prove a color of push and pop. For that, we'll need a postcondition to be able to call push and pop in sequence and know the effect, so that it's safe to sequence these calls. So here we can just add a simple postcondition on push that states that the size has been increased, and a simple postcondition on pop that states that the size has been decreased, with again a simple definition of size which relates to the value of this top marker. It's just s.top here. So let's look at that. So we have this stack here with precondition and postcondition not added yet, but you can see that already I put all the contracts on the type. And if we just analyze the stack as it is now, indeed, we cannot prove that accesses in the push and pop subprograms are safe. So there might be buffer overflows here. So what we want to do is to add this precondition that I mentioned. So here, and when we reanalyze these units with precondition, now it's safe. That doesn't mean that we can prove a user of the stack. And indeed, if we call Spark on this procedure use stack, which creates an empty stack and then pushes values and pops a value, after the first push, we don't know what's the state of the stack because we're missing a postcondition here. So let's go back to stack and add the simple postconditions which I mentioned. that just states what happens on the size. Again, we can analyze just the implementation of the stack. It's proved. And we can come back to the user of the stack. And here, we can safely call push and pop in sequence as we want. One last thing. Here, let's add something a bit more complex. So there's a condition here to push values on the stack. So it turns out that this condition is always true. So indeed, 5039 is a prime number because it's factorial 7 minus 1, one of these known prime numbers. And we can, it should prove because we're always getting in the if branch here. But if we call the prover as we did before, it doesn't prove the call to pop. So it doesn't know that we're going always through this branch. There's an easy solution here, which is to push the proof level up, so to level 2. And in that case, it proves. So what happens? Let's see. What happens is that some proofs are harder than others. So here it was slightly harder to show that, yes, this function is prime, always return true on this value, factorial 7 minus 1. And so they require more time or more provers for the automation to kick in. And there are a set of switches that can be used with the Spark tool. So first, the timeouts given to provers to achieve proof can be augmented. Then the number of provers that are used can also be increased. So we have up to 4 provers, and they can be used in combination. And finally, there's a level switch, which I just used in that studio, to set what we call the proof level. And among others, this proof level will decide what timeout and prover are used. So at level 0, which is the default in that studio, just one prover is used, CPC5, with a timeout of 1 second. And so that was not sufficient to prove the harder case that I just showed you. Then at level 2, all 3 provers, CVC5, Z3, and AltaGo are used with a slightly longer timeout of 5 seconds. At level 4, all 3 provers with a timeout of 60 seconds. But of course, you can combine these and set lower level switches like timeout and prover in addition to level. So that was all for this proof of memory safety. And we'll have a next webinar on proving software security. So now the floor is open for questions and answers.
Thank you, Yannick. We have one question that was asked by Weston Pan. So Weston says, I am surprised that memory leak is not statically checked. I assume that the borrower ownership restrictions would cover that. I did read somewhere that Rust also allows memory leaks. And then Weston asks, is it due to the same limitations?
So Weston, so maybe I was not clear. Memory leaks are checked by Spark. So of the checks that were under the memory availability kinds, the other checks, so running out of stack space or running out of heap space or fragmented the memory, are not checked by Spark because they are checks that are related to how the whole program behaves with respect to the available stack or heap space. But memory leaks are checked. So there are checks inserted, like we just showed, for all cases of memory leaks, when assigning into a variable that already holds a pointer to an own data, or when a variable which may own data ends its scopes. So you will get checks in Spark for this.
Okay. So that's the only question that we have. I'll wait a little bit and see if there's any other questions that anybody would like to ask. Again, you can use the question interface in the lower right-hand corner. While we're waiting, just to confirm, everyone who signed up for today's session will receive a recording of the events and a follow-up email. So please look out for that. and you can download the slides right now using the handout section, which is also in the bottom right under the Apps tab. Our previous webinar in the series, Spark Pro for Embedded and Systems Programming, is also now available for you to watch on demand. So Weston asked a follow-up question. When there's a timeout, are you allowed to continue where it left off?
So there are two elements to that. For the general proof of program, indeed, everything that has been proved is saved. So there's a session file that you can even put in the version configuration that saves how every one of these checks in your program was approved. So this means that when you rerun the tool, it will not start from scratch. It will only prove things, attempt proof for things that have not been proved yet. The other part of the question is for a given check, if the check was not proved, we don't save the internal state of all the provers that I mentioned. So if you try with a longer timeout, then the provers will be called again on the same check with a longer timeout, because there's no internal state in these provers that is saved here. But the more important part is that all the things that were proved are still available, and so it leads to a very natural interactive use.
Okay, Philippe says, a general thought, if I permit, I see three advantages of full proof. First, runtime checking is no longer required. I agree. Second, because of the above, a zero footprint application and thus more compact code and faster code can be achieved. Again, I agree. And third, the dream of zero bug applications could more or less be achieved. And again, I agree. Now, having said that, I'll say that this does assume that you have fully proved everything that you need to convince yourself that there's zero bugs. And really, we're going to be talking more about that in the third webinar series. So we'll mention that in a moment when we thank you all for attending this one, where we'll talk about proving program correctness. But certainly for the first two, runtime checking is no longer required and a smaller footprint application can be achieved. Yes, this is definitely an objective in using Spark. So thank you for you. Mikhail asked a question. Thank you. I was surprised to see that a SAT solver like Z3 is being used in the background for proving. Does this mean that proving correctness is related into solving SAT or really SMT formulas? Any?
Yeah, so Z3 is really an SMT solver. So it has a SAT core for solving satisfiability problems. But around that, so SMT is satisfiability modulo theories. There's a number of theories to handle what we have in programs, in particular arithmetic of various kinds. So integer arithmetic, floating point arithmetic, bit vector arithmetic. And so we use all of that. And indeed, we are translating the checks that I mentioned into formulas in this SMT-lib format, which is used by the different provers that I mentioned. So this problem is reducible to satisfiability of SMT formulas.
Weston has a follow-up question. Do you recommend placing the proof artifacts in version control?
So yes, when you want to save the results of a proof and share it between various users, you can share the session files that I mentioned. So we do that, users do that. And this is a possible way to reduce the running time of performing the proof. In other contexts, you might want to redo the proof completely, and that's also possible. And in that case, you're restarting from scratch without these session files that I mentioned. And these, by the way, these are text files, so they can be put into version control easily.
Okay, Derek asks a more general question. Why is so much why is so much effort going to Rust development at Ada Core? with a parenthetical considering that the language definition is not stable. I will not say much about this because this is really a call on Spark. I'm also the product manager for Rust. If you would like to talk to me about Rust, I would be delighted to have that conversation. I will say, why are we paying attention to Rust? Because we think we have something unique that we can offer the community. Our customers are asking us to add support for Rust. And honestly, we don't want to just pretend that there's only one tool that solves every problem. So Weston, I appreciate your comment that Rust is considered more cool and Ada and Spark are not getting the attention they deserve. I agree. I would be delighted if everyone on this call just went home and yelled about how great Spark is and how fantastic Ada is, but that doesn't need to undercut our Rust story. I think there's enough room in problem solving that both of these technologies have room to grow and have room to gain market share. So enough said on that topic. So we have a question from Thomas. Can I use delta aggregates to show which component of a record is initialized after a procedure?
Yes, you can state in your postcondition that an output is equal to the initial version, I guess, of the same parameter with some components initialized to this and that value. So yes, that should be possible by just using a delta aggregate in the postcondition.
Okay, do we have any more questions? I'll wait a couple of minutes here before we close down the events. As I said a moment ago, if you're interested in seeing more about proving program correctness, we are going to have an upcoming webinar, and this will be the final in this three-part series, Proving Software Security with Spark Pro. So we're going to take a step beyond talking about memory safety, and we're really going to look at how you can formalize security properties and then prove those formalized properties using Spark. Weston has a good question. Given that some programs have to be compiled for multiple targets, do you have to run proofs for each target?
So in general, yes, but that should be automatic. So if your proof depends on the particularities of the target, the size of integers, for example, the alignment, then you need to rerun the tool with the specification of the target. And this is done automatically by the tool, which selects the runtime and targets that you're specifying for your project. So that's what I showed in the first session of the webinar. That being said, proof is automated once you've put the efforts in adding the right contracts, like I showed during this session, which means that if the proof is independent of these small details in target parameterization, then once it has been done for one target parameterization, it should just fall through automatically for all other targets.
Okay, thank you, Yannick. Thank you, everyone who attended. Really appreciate having you here. Look forward to seeing you at the next webinar, Proving Software Security with Spark Pro. I hope you have a wonderful day.
Thank you all.